Guys, my name is Marzanul Islam and this is my Physics 2212 Lab 5 presentation on magnetic molasses. So for the introduction for this lab, the purpose of our lab is to collect and analyze data of a bar magnet falling through an aluminum tube and comparing it with computational models. We'll use this data to estimate and show how Faraday's law works. The fundamentals we'll be using are Faraday's law, the Biot-Savart law, Newton's second law, the time derivative of magnetic flux on dipole, and the magnetic force. So there are images of these formulas listed on the right side. And as a preview of our results, the experimental time we got from our trials were 1.21 seconds, and the computational time from our glow script model was 0.8115 seconds. So for the model, the magnet was used to model a magnetic dipole, while the aluminum foil modeled the tube through which it fell. For our assumptions, our air resistance acting on the magnetic field was negligible. Gravity and magnetic forces are the only forces that were acting on the magnet, and the bar magnet acted as a dipole. So for the procedure, first we found the magnetic north pole of the magnet and then dropped the magnet down an aluminum tube 5 times and then calculated the average time it took for it to fall through the tube. So as you can see on the right side, this is a real life demonstration of the experiment. Our system is the aluminum tube and the magnet, and the surrounding is everything else in the room. So for experimental data, here are the trials and the different times we got for each of the 5 trials. And for our tube dimensions, we have the length, the width, the inner radius and outer radius of the tube. And for the magnetic properties, we have the mass of the magnet and the magnetic dipole of the magnet. And then we have our average time here. So a few checkpoint questions. So why can't we use a ferrous tube, for example, a steel pipe? Ferrous tube made from steel will have magnetic properties and would skew our data. And what happens to the magnet? How does this compare to a magnet falling in free space? So the magnet falls slower through the tube as there is an upward magnetic force due to induced current. So this is our computational glue strip model. So as you can see, we're defining our physical constants in the first part, and then here is the code for our velocity versus time graph, and then we're entering our variables which relate to the dimensions of the aluminum foil. And then as you can see here, we're just applying formulas to get the specific values we want. And then finally, this is our result. So this is our velocity versus time graph. And here is our model of the magnet falling through the bar, through the aluminum foil, but you can't really see it since it's just a static picture. So as you can see, the time we got from our computational model was 0.815 seconds. So now interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate currents flowing in opposite directions. Which color responds to which current? So according to Lenz's law, red current is counterclockwise and blue is clockwise. And what happens to the dynamics of the system when you flip the magnet around? Flipping the magnet around would not change anything, but only the current direction would be changed, but it would fall in the same time. And how does the total time in the tube of your real world simulation compared to that of your computational model? So the computational model is slightly shorter. This may be due to air resistance and human error in timing. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar? So gravitational force is greater than the magnetic force when exiting the tube but equal inside. So if we go back to our graph, and this middle part, as you can see inside, it's the gravitational force and magnetic forces are the same. So possible sources of error: the stopwatch was not precise and human error may have been present, and air resistance may have had an effect on the magnet falling. So for our what if and why questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So lower resistance would increase induced current, creating a stronger opposing magnetic field, and magnet would take even longer to fall. So this is because of Ohm's law, which states that the voltage is equal to the current time resistance. So a lower resistance would mean to create the same amount of potential difference, our induced current would have to be higher, and then this would cause our magnetic field to be greater and the magnet would take even longer to fall. And what if holes or slots were cut into the tubes? How would this affect the ring currents? So less current rings would be present in the tube, which would make an overall weaker opposing magnetic field, causing magnet to fall faster. Basically, our magnetic field lines would be escaping the aluminum foil tube, and this would lower the magnitude of our magnetic field, and this would decrease the magnetic force on the bar magnet, which would cause our magnet to fall faster. So that's it for my lab. Thank you for your time.